Hello, my name is a.c.atkinson.
And my name is Marco Riani.
This afternoon, we would like to talk about the analysis of transformations taken from our forthcoming book, made together with the three co-authors you can see up there.
So we are talking about the transformation of the response that we hope that you have already seen the video about introductory video about transformations. The first data set that we are going to analyze is called the hospital data.
Nita and some other people analyzed 108 observations on the times of survival of patients who had a particular kind of liver surgery. There are 4 explanatory variables in this, and you can see that there seems to be a relationship between Y and all 4 of the X's. These data are in the original form. Nita and his co-authors analyzed the data having taken logarithms. This is a perfectly reasonable and standard thing to do when analyzing survival times, but we would like to use the methods of the forward search to see whether in fact it is reasonable in this particular case.
Now we compute the score test for transformation for the 5 most common values of lambda, which are -1, -0.5, 0, 0.5, and 1.
So that is the most commonly used values for the Box-Cox transformation of positive responses.
From this plot, we can see that the log transformation, the curve, the trajectory associated with the score test for log transformation always is inside the confidence bands. On the other end, the trajectory associated with lambda is equal to 1 then starts going out of the bands already when you have about 65% of the data inside the subset. So log transformation indeed seems the best. The additional benefit of this plot that once again you know the percentage of observation which is in agreement with a particular transformation.
Another appealing property of this particular plot is the symmetry, really, of -0.5 and 5 and -1 and 1 about the trajectory for 0. This plot therefore justifies the decision of the previous authors to take a logarithmic transformation for these data.
Now we move to the analysis of the loyalty cards data. We start with a plot of the response, which is the amount spent over a certain period of months in the supermarket as function of the number of visits, the age of the loyalty card owner, and the number of components in the family. Well, we see that there is a clear relationship between the number of visits and the amount spent. So it is important that people go inside your supermarket, because the more they go, the more they are going to spend in the supermarket. Okay, what is the best value of the transformation parameter? Here we use a grid from 0 to 1, a grid of values of lambda with step 0.1. Let us see the firm plot.
So the question is, why have we taken a finer grid in this case? Started with an initial coarse grid, and this would have included 0.5 and 0, and you can see that they are both very widely spread either side of the central band. So we therefore, to get any information, had to take a finer grid.
And look at the difference between 0.3 and 0.4. The trajectory for 0.3 goes out and then comes back again inside the bands at the end. On the other end, the trajectory for 0.4 always is inside and then in the final step goes out of the boundary. So now we transform the data using 0.4 and we analyze the data using the transformed scale. You see that now we transform the data using 0.4 and now we apply on the transformed data our outlier detection procedure. In this y-axis plot, you can see the units which are declared as outliers. These units are characterized by a set of customers which, given their high value of x1, given their high number of visits, they tend to spend less than the other customers, given their large amount of visits. On the other end, while the outliers here form a clear pattern in x1, it is not very clear the pattern in the other two explanatory variables. Now we also show the minimum deletion residual with all the bands, and then highlighted in red are the last 18 steps where the 18 outliers enter the search. Notice that at the end there is the masking effect. At the end, the trajectory of the minimum deletion residual is inside the bands. Therefore, once again, a backward analysis could suffer from masking. You see, now we have the monitoring plot of residuals. In this monitoring plot of residuals, we see that the outliers are characterized by large values, large negative residuals. It is also possible to have a personalized data tip, in the sense that if you click on the trajectory, then you can see the number of the unit, and then when the unit entered the subset. What is important to see is that the pattern here. You see that these units, this set of outliers, which are characterized by very large residual, in the final step they have a residual which decreases. Due to, on the other end, we have the opposite thing for the so-called units which are on the other side of the regression plane. If you now see therefore the plot of the transformed sales against x1, this repeats what we have just seen, that indeed they form a cluster. You can imagine that as the outliers, these red crosses, enter the subset, the estimate of beta for x1 decreases. In fact, the monitoring of the beta coefficient for the first explanatory variables, which is the number of visits, has a sudden decrease when the outliers join the subset. Let us move now to the third example, which is the one referred to the investments funds data.
So the purpose of this is to relate the medium-term performance of 309 investment funds to two indicators. Of these funds, 99 have negative performance, so we have to extend our modeling of the transformation. The data come from an Italian newspaper. The response is the medium-term performance of 309 investment funds to two indicators. First indicator is the short-term 12-month performance of the bonds, and X2 is the short-term volatility. Performance is measured as the percentage change in the price of units of the fund.
Now we repeat the plot, the previous plot, but now we have two colors. So we have distinguished the funds with positive performance from those which had a disappointing
Performance.
result.
One can see that if there appears to be a strong relationship for the positive responses, but much less strong relationship between the negative responses and the explanatory variables.
Now what we do is a plot, as we have done before, considering a grid of values of lambda from 0.5 to 1, because you can see that both 0.5 and 1 are on two opposite sides, so you really need a value of lambda which is in between. Note that here we are talking about a unique value of lambda. But the question is, the behavior of the funds which have a positive performance need the same transformation parameter as the funds which had a negative performance? To answer this question, we compute the extended score test. That is, we repeat the trajectory of the score test for lambda is equal to 0.7, but we add two additional tests.
We use the same, for the moment, we use the same value of the transformation parameter, but we test just for the positive observations and just for the negative observations to see whether, in fact, the value here, 0.7, is appropriate for both of these subsets of the data.
If the value of 0.7 is appropriate for both sets of the data, these three tests are very close to each other.
So the three trajectories will be pretty much on top of each other.
Right, as you can see here at the very beginning. Then they start to depart, and their degree of departure increases as the subset size increases. This is an indication that you need two different values of lambda. And then given that the test for positive is above the test for negative, this indicates that positive values need a transformation parameter which must be bigger than that for observation that have a negative performance.
Just recall that for the fan plot from the Box-Cox transformation, the trajectory for 1 is usually at the bottom and the trajectory for -1 is at the top.
So now, given that we have seen we need two values of the transformation parameters, then here we start analyzing whether we can proceed with 1 and 0.5, respectively, for positive and negative observations.
So these parameter values are taken because they lie either side of 0.7.
Right. You can see that these two values lead to a trajectory which is not inside the bands. So instead of 0.5 for negative observations, so we consider 0.25, and you see that the trajectory is better. And we are doing even better if we consider 1 and 0. You can see now that there is an agreement between the three tests. This has been done in a non-automatic way, but we also have routines for doing it in a fully automatic way.
Another thing to notice about this too is that nothing happens towards the end of the search. There is no evidence that there are any outliers. The trajectories don't suddenly part from each other.
Now we see a scatter plot of the transformed data using these two values of lambda. Maybe we want to compare the scatter plot of the transformed observations with that based on the original observations. So on the left you have the original y-axis plot, on the right you have the data, the y-axis plot when the data have been transformed.
We are fitting regression models, and it is clear that the data on the right, in the right-hand panel are appropriate for a regression model. There's no evidence of heteroskedasticity, whereas in the panel on the left, the data have a variance that depends in a not particularly smooth way on the values. Right. The right-hand panel has a very interesting structure, and if we knew more about the data, it would be interesting to try to see whether there is some variable on which to cluster the positive responses. Unfortunately, we do not have such information.
Now we end up with a table, which is table 6.1, which compares the value of adjusted R-square for original transformed data, data transformed according to 1 and 0.5, and then this is our preferred transformation, which is 1 for positive and 0 for negative. As you can see, moving along from the left to the right, the value of adjusted R-squares increases from 0.78 to almost 0.82. This concludes the analysis of this data, and now we move to the analysis of balance sheets data. Once again, we start with the plot of y against the 5 explanatory variables.
The data are taken from balance sheet information on limited liability companies, which, unlike the investment funds data, we will discover do indeed include outliers. The response is the profitability of individual firms in Italy. There are 998 observations with positive response and 407 with negative profitability, making 1,405 observations in not all.
We start with the FEM plot for values of lambda from 0.5 to 1.25 with a step of 0.25. This plot shows that if we consider just a single value of lambda, the trajectory for lambda is equal to 1 is inside the bands. Well, on the other end, at the end, there is, let's say, a big fluctuation. Goes from being below the envelope to being above. Before, do we need 2 values of lambda, or we need just a single value of lambda? Let us repeat the plot now with the other 2 tests. Note that before, the green trajectory, which is associated with testing for positive, now is below. Mm-hmm. And this indicates that the positive observations need to have a value of lambda which is smaller.
Whereas the negative observations need to have a larger value.
Correct. And the distance between the 3 tests, which tends to increase as the subset size increases, suggests that indeed you absolutely need to treat the 2 tails in a different way, with the 2 different values of lambda. Now, these are the data with the new extended FAM plot, when you have transformed the data using 0.5 for positive observations and 1.5 for negative observations. This plot says that there is still a difference between the tests. And then there is a set of probable, possibly outlying observations that completely change the value of the score test. We compare the fit in the original scale, no transformation, and the fit when after deleting the outlying observations. What is immediately comes out is the big difference in the adjusted R-square, which goes from 0.5 to something like 0.69. As concerns the t-statistics, the significance of the t-statistics for transformed data has increased. So we can now do something interactive for this balance sheet. And now if we monitor the residuals, and this is on the left, there is the minimum deletion residual. On the right, there is the plot of scale residuals for the transformed data. And now we can brush this plot in order to understand the position of the units which have very, very large residuals. And by our automatic procedure, we end up with 42 observations. Here we just brushed a certain number of observations. Then the observation brushed, as you can see, they tend to enter the final step of the search. And they cause a big increase in the trajectory of minimum deletion residual. Finally, notice there are two sets of lines, that is the fit with or without the brushed units. So you can have an idea about how your regression hyperplane changes. Now, given that so far we have done things in a non-automatic way, now we want to run our automatic procedure. These are the loyalty cards data, now using the five most common values of lambda.
Okay. The red bars at the bottom tell us how many observations are used in the fit, so that it's only at 0.5 as a reasonable proportion of the data included. For all other values over this grid of lambda, a large number of outliers are detected.
And we have two criteria for defining the best value of the transformation parameter, a BIC or an agreement index. The agreement index roughly checks how close to zero is the trajectory in the central part of the search. And these two criteria agree that if we consider just the five most common values of lambda, 0.5 is the best value of the transformation parameter. Now we consider a finer grid. A finer grid from -1 to 1 with a step of 0.1. And remember that before we had found that the best value was 0.4. Now we have the same information in a fully automatic way. We're using both BIC and agreement index. Note that from lambda is equal to -1 up to 0.2, you detect a very high proportion number of outliers, then with 0.3, and then 0.4. With 0.4, you end up excluding a very small number of observations. And 0.4 indeed seems the best value of the transformation parameter.
In three ways, in fact, in the two indices and also in having the smallest number of outliers identified.
This automatic procedure, which has been used for the loyalty cards data with just a single value of lambda, in the book is also described when you have two values of lambda. Thank you for watching.
Thank you.